Alright, question 1. What is the RMS value of a current? The RMS value of a current, if you see the definition here, is the equivalent constant DC. Constant DC that gives you the same average power dissipated in a given resistor. Now, what does this mean? For a AC, you know that the current is going to fluctuate up and down like this, right? So if you consider that power is equal to I squared R, for example, then that means that your power, right, is not going to be a constant value. The power dissipated in this resistor is not going to be constant. It's going to fluctuate as well. How will it fluctuate? As per this graph, okay? This is a sine squared graph. So it is useful for us to be able to define the average power, okay? Peak power is not always the most useful thing. So what it means is that if you look at this graph here, that means that for a given AC, right, that is defined by its peak power like this, there will be an equivalent DC level, right, which will give us the same average power, okay? And our job is to find this equivalent value of DC that gives us the same average power. Question 2. Why is there a need to find RMS instead of just using the average current? Okay, now some of you might know this already, but please bear with me. If you find the average current of a sinusoidal AC, then your average current is going to be equal to 0. Why is that the case? If you look at the sinusoidal wave, for every possible positive value that you have here, all these positive values, right, there's going to be a corresponding negative value as well. So if you want to find the average value, right, between here and here, it's going to be 0. And so on for here and here, and as the wave continues, okay? So we just find the pure average, the pure mean. It's going to just give us 0 every time, which is not very meaningful, okay? So that's why we have to do this RMS thing, root of mean of squares, okay? Now what does RMS mean? Will be covered in the next part. Okay, so question 3, how do we calculate the RMS value of a sinusoidal AC? Now, before we go into that, let's break down the term RMS, root mean square. Now, root mean square literally means root of the mean of the squares, okay? So, let's say our current, right, we call it I, then the square of current will be I squared, okay? So, we have some I squared values, right, because remember, I is fluctuating sinusoidally. Then what we do is we find the mean of these squared values, mean of square of current values. And then finally, what you want to do is to find the root, the square root of the mean of the squared values. Okay, and that is what we are going to do in a step-by-step process. Okay, so let's take this through step-by-step for sinusoidal AC. So step 1, we have our AC like this, right? And what we're going to do is we're going to square the values. Now, bear in mind that in this case, I'm going to show you everything graphically because I find that this is the best way to visualize what is going on as opposed to just throwing equations at you. So if you are just picking up this topic for the first time, please do yourself a favor and draw out the graph, okay? Step by step, just like what I'm doing now. Follow the logic. Okay, so like I was saying, first what we do is we take our AC graph, right? And we find the square, right? We square the values. So if we square all the values here, we end up with a graph that looks like this, a sine squared graph, okay? Simple enough. Step 2, find the mean of the squares. Now this is the critical step, okay? Because what we're going to do is from this sine squared graph fluctuating values, right? We're trying to find one constant value that can represent the average value. Okay, now how do we do this? This is the trick. What we're trying to do is we're trying to find a value that gives us the same area under graph as the fluctuating value. So if you look at the diagram here, what I mean is that the value of this mean of squares, right, the mean squared value of the current, should be such that this area, this green shaded area here, is equal to the total red shaded area on the left. Okay, that is the key point. And regardless of what kind of variation you get, it always boils down to this. Okay, the two areas must match. So what is the value of this mean squared current that will satisfy this condition? It turns out that the value is half of the peak value. So if we have a peak current over here, peak square current, right? If we find half of this value, right, this is an appropriate value that will satisfy the condition. Why? Because if we draw this line through like this, you can see from the diagram that I've drawn out here that the areas are equal. The area under graph for the red line and the green line, they are equal. Okay, so our mean square value turns out to be peak current squared divided by 2. So all that remains is the last step. Okay, now that we have the mean square, we want to find the root of the mean square. So we take the previous value and we square root it. Okay, so we have our mean squared value, I naught squared over 2, and we square root it. This will give us our final RMS value of I naught over square root of 2. So now we're going to look at how to do this for half-wave rectified. So half-wave rectified is when you pass the AC through a diode. Now as you remember, diode only allows your current to travel in one direction and it stops the current in the other direction. So let's say it stops the current in the negative direction. What we're going to see is that this portion of the graph, the negative portion of the graph, is going to disappear and be replaced with a 0 throughout. Okay, but this does not change our approach. We still follow the same 3 steps. Step 1, square the values. Okay, so we still have these 2 positive portions, right? So these 2 get squared, right, into these 2 shapes here, and then 0 gets squared into 0. Okay, so we end up with a I squared graph that looks like this. So still following the same steps. Step 2, find the mean of the squared values. Now, the area, you can see the area is half of before because originally we had these 2 more here, right? But now these 2 are gone. Okay, so the area here is half. Now, what is this value here that will have the same area under graph here as these 2 peaks? If you think about it a little bit and you compare it to the previous graph of the full wave, you will be able to come to the conclusion, I hope, that this value is equal to I naught squared over 4. Okay, because the area here you can see is half of the previous area. So if the previous level was I naught squared over 2, this one should be I naught squared over 4, which will give you half the area as well. Okay, now if you cannot understand it from that standpoint, then take a look at these diagrams that are drawn here. Basically what's happening is we can do some redistribution of the area again, right, to this level, I naught squared over 2, but this will only give us 2 blocks like this. We still have some empty space over here. So we still need to redistribute it one more time like this, okay? And then this will give us our value I naught squared over 4. For a half-wave sinusoidal, the mean squared current is equal to I naught squared over 4, where I naught is the peak current. So the last step is very easy. Step 3, find the root of the mean squared values. Okay, so you just square root this I naught squared over 4 and it will give you I naught over 2. So the IRMS in this case for a half wave is equals to I naught squared over 2. So when you're doing your practice questions, whatever variation you find in how the alternating current graph looks like, all you have to do is to stick to these main ideas. Okay, number 1, square the values. Number 2, find the mean of the squares of the values. Now, what does the mean of the square of the values? You're just trying to find a straight line that gives you the same area on the graph as your original I squared graph. Okay. After you find that value, just square root it. Okay, and then that is your RMS value. So I hope you found this mini lesson useful, and I'll see you again in the next video. Thank you.